sacred institutions. Bedroom eyes, they call them in a bygone day.
Hello, and welcome to Physical Attraction, the show that explains physics, one chat-up line at a time.
But for corrupting others to a life of carnal pleasures and lewd designs. A man whose erotic desires and libertine practices are used to titillate the unsuspecting and would stoop to any depth.
Hello and welcome to this episode of Physical Attraction, where I will be explaining antimatter. Physicists love symmetry. Symmetry means that you can change a system in some way and it will still be the same. So reflectional symmetry is the one that most people understand. Something's the same when you reflect it in a mirror. But there are other symmetries too. Now for physicists this isn't just some kind of weird fetish, although to hear physicists talk about it you might think that it was. When they start drooling about the glorious and beautiful symmetries that underlie everything, you can begin to question whether the interest is purely mathematical. But symmetry is mathematically useful. It can hugely simplify your equations and the problem that you're trying to solve. Imagine drawing a map of a world that you know to be symmetrical. Well, then you only need to see half of it, and understand the symmetry, to have a map of the whole. The symmetry cuts your work in half, and it can simplify so many problems. By mapping the laws of physics in our little corner of the universe, and then expecting what's called translational symmetry, or systems that work in a similar way across different locations, it allows us to make calculations that apply across the world, across the universe, just from experiments that are done here on Earth. Conversely, if the laws of physics weren't the same pretty much everywhere, we would struggle to calculate anything of use. In fact, most of the laws of physics, as we know, can be derived just by looking at a system and thinking of its symmetries. We'll come onto this in a future episode because it introduces the profile of one of the most famous and one of the most important physicists of all time, Emmy Noether. And more than this, even though physicists say they're motivated only by the empirical evidence, that's not strictly true, I don't think. I think all of them have a view that an ideal world should be symmetric. Maybe this is because the pool of people who become physicists is a little bit biased. You might want to study physics because you find mathematics beautiful, or you find the world to be beautiful, or you find symmetry to be beautiful, or all three. And then you'd want to discover a universe with symmetry, because symmetry is beautiful. From a philosophical standpoint, if the universe was created, we hope that the creator would make it logical, something that makes sense, something that's beautiful. And if it wasn't created, if you're the most cynical person ever, who doesn't believe in gods or reasons or any of this namby-pamby stuff about things being beautiful or ugly, then there's still a reason to expect symmetry in a lot of cases. It's kind of like the anthropic principle in philosophy. You remember the one that's the solution to the Fermi and Drake paradox that we talked about in the Fermi and Drake episode. We exist, humans exist, and although it might not always seem like it, we're fairly orderly and fairly structured creatures. If the universe and the laws of physics were a confusing, asymmetrical mess, it probably wouldn't be good news for any stable order that tried to exist. Let me give you a concrete example to explain what I'm saying here. Imagine that particle physics wasn't symmetric, so say that the charge on a proton was much higher than the charge on the electron. Then you'd struggle to have electrically neutral atoms, and you wouldn't have the complex chemistry that comes from them that gives rise to life. Similarly, you can imagine that the force law for charges might work differently. What if like charges repelled each other stronger than opposite charges attracted each other? Disturbances to symmetry could do more than make the universe ugly. They could make it completely unworkable. But then we shouldn't be so fast to discount asymmetry, imperfection, things that aren't symmetrical, little imbalances that don't make sense. Happiness, joy, ecstasy, love. These are all chemical imbalances in our brains that will, in the fullness of time, be corrected and return to a baseline, a zero. Your personal zero may vary, but that's the way of things. All of our exuberant joys, and all of our heart-rending sorrows, in other words, the very things that make us all human, All of these are asymmetries. As are we. As is everything. Because one of the unsolved problems of physics is why the hell anything actually exists at all. See, everything we know is made up of matter. All the physical objects, all the clouds and sheep and people and chemicals and rocks and water and trees and buildings, the stars, the galaxies, everything. It's all composed of these subatomic particles that make up matter. And there's a conversion between matter and radiation. A highly energetic photon of radiation can produce matter. So if the universe began with energy in the form of radiation, perhaps, matter can follow from that. This equivalence between energy and matter is what the famous equation E equals mc squared means. The energy that's intrinsically in something that's massive is the same as the mass of that object multiplied by the speed of light squared. That's what Einstein was on about. But there's a problem. When photons turn into matter, they produce two particles. The photon needs to have twice as much energy as the particle, whether it's a proton, electron, whatever, that you want to produce. Each particle, then, is produced with its antiparticle. For each electron made, there's a positron, and for each proton, there's an antiproton produced. The antiparticles have the same mass. They look the same if we could see them. They behave in similar ways under most of the laws of physics, but they have the opposite electrical charge. And this makes perfect sense too, because we believe that things like electrical charge should be conserved in the universe. They can't be created or destroyed. That's a form of symmetry too. We can't have photons which have no charge, randomly turning into protons that have positive charge. Then we'd end up with an imbalance where there's more positive charge than negative, which would ruin everything. One of the ways to see this is by realising that on large scales, the dominant force seems to be gravity. So that's why, for example, the main thing you have to think about when you're considering the structure of galaxies or stars is actually gravity, because gravitational collapse that draws in stars and galaxies together seems to be the dominant force. You don't even take into account electromagnetic forces in some of these things. So for example, in our very first episodes, we talked about how stars are born due to gravitational collapse. But gravity is a weak force compared to electromagnetism. If for some reason the universe was making more positive charges than negative, even if it was just 1 in a million, stars like the Sun couldn't possibly exist. The electromagnetic repulsion, which is far, far stronger than the gravitational attraction, would tear them apart without a doubt. The universe as a whole would probably explode, with everything driving everything else apart far faster than gravity. Only a tiny, tiny imbalance could possibly be permitted without changing all of our observations. So it makes a lot of sense that we posit that the overall charge of the universe is 0. And if that's true, then we can't have any processes that make charge or destroy it. Every process has to keep charge the same. And every process we see in the universe does keep charge the same. We never see electrical charge being made or destroyed. But that can only work when you're converting a photon into particles, when you're converting energy into matter, if each particle is made with its antiparticle. One way of looking at antiparticles that was popular originally is like they're holes in particle space. Imagine that there's a huge sea of electrons, say, that all have negative energy. When a photon interacts with this sea, it can push an electron from this negative energy sea into existing, with positive energy. But the hole is left behind, and if the electron ever hits this hole, or another one does, it will fall back down again, releasing its energy once more as photons, and this is what we call annihilation. When a particle meets its antiparticle, they annihilate each other and turn back into photons of energy again. So the fact that photons can turn into a particle and antiparticle with opposite charges is pretty crucial. It means that radiation can turn into matter without messing up charge conservation. But there is a serious problem, because when a particle collides with its antiparticle, they annihilate each other and turn back into photons of energy. Or photons collide and they turn into particles with positive charges and negative charges. So you can see the process is symmetrical. It's symmetrical in time, if you like. You run it forward and the photons turn into an electron and positron, say. That's pair production. You run it backwards and the electron and positron turn into photons again. Nice and symmetrical. But you can see the problem. Why is there any matter at all? Why didn't all the antimatter that was produced just annihilate it? After all, we're not running around in fear of annihilation from antimatter, just the incompetence of our political leaders. In fact, when we look at the universe around us, there are no large-scale structures made of antimatter. There are no anti-stars, no anti-people, no anti-planets. Antimatter is incredibly rare on Earth, and it usually only exists for a few fleeting seconds. We only discovered antimatter by looking at rare cosmic rays from outer space. And when it's produced on Earth, for example, in our particle colliders, it doesn't take long before the antimatter collides with some matter and annihilates, disappearing again into energy. This process is very destructive. If you and anti-you ran into each other, the result would be an explosion with the power of 10,000 nuclear bombs. When nuclear weapons get used, only a small fraction of the rest mass energy is converted into the explosive power behind the bomb. With annihilation, you get all of the rest mass energy converted into radiation, which is far more powerful. It would be a massive explosion and a serious problem. So it's a good job that antimatter is rare in our part of the universe. But this is weird because the processes we know and see in the world around us produce equal amounts of matter and antimatter. So why does matter dominate? Why is there more matter than antimatter in the universe? Why aren't we just a soup of particles and antiparticles, annihilating each other and being produced endlessly, in a symmetric but ultimately boring mess? So the whole fact that anything at all exists is down to some unexplained asymmetry in the early universe. At some point things weren't neat and tidy and symmetrical. Something happened to make sure that slightly more matter than antimatter was produced. Most of the matter and antimatter produced around the time of the Big Bang annihilated each other, but a tiny leftover remnant due to an asymmetry in the laws of physics meant that we ended up with matter dominating and not antimatter. Maybe it was only one particle in a billion, or one particle in a trillion, but the universe for a while had a slight favourite. It favoured matter, and hence, due to the slight asymmetry, everything around us can exist. I'm reminded, whenever I think about something like this, of that brilliant song lyric by Neutral Milk Hotel. How strange it is to be anything at all. By the way, one of the things that you might have thought, and that I remember thinking originally, is, well, why do we assume that there's no antimatter out there? Why do we need to assume that there's no antimatter galaxies out there? Why don't we just say, maybe there's loads of antimatter in the universe and we just got somehow separated from it, rather than having asymmetric physics in the early universe? Could there be anti-stars and anti-atoms out there? And if so, what would happen if an anti-Milky Way crashed into us? Well, we actually know that anti-atoms can exist. In fact, we've made some of them in our particle accelerators. The only problem is that everything in our universe that we know wants to annihilate them, since they're made of matter. So you can see how this might be a pretty big problem. But we have created atoms of antihydrogen. Hydrogen is the simplest element. It's just one electron and one proton. So its antiatoms were the easiest to create. You just need to have a positron and an antiproton and have them orbit round each other. But if you're hoping to annihilate your enemies, you're probably better off buying a gun, because antihydrogen costs $90 trillion per gram to produce. Obviously they've never produced a gram of it, only tiny amounts. It is the most expensive material on the planet. So while the physics of antimatter seems to check out, and in principle you can imagine an anti-universe with anti-people and anti-politicians who maybe occasionally tell the truth, it probably doesn't exist anywhere in our universe. Almost everything would be the same for these anti-people in their anti-worlds, except what they call positive charge would be our negative charge, and a few similar things along those lines to do with right and left-handedness. It's a tantalising prospect. Because of the symmetry, antimatter looks exactly the same as matter. It's not as if it would be the opposite colour or emit anti-light or anything like that. In fact, they've actually looked at the antihydrogen atom and demonstrated that it was similar to the hydrogen atom. So if you had a telescope, observing an anti-galaxy would probably look the same as observing a galaxy. And this makes sense, right? Because we've talked about how electromagnetic photons turn equally into matter and antimatter. That's this symmetry. Electromagnetism treats matter and antimatter like the same objects, and since light is just electromagnetic radiation, we know that they should look the same. So it might not be obvious if we were looking at anti-galaxies. Paul Dirac, the genius quantum physicist who first theorized that antimatter should exist, speculated that there might be regions of the universe that were dominated by antimatter. But the problem is that if there were big chunks of the universe made out of antimatter, there would be some frontier where the matter part of the universe that we live in and the antimatter bit collided with each other. And that frontier would produce huge amounts of high-energy gamma rays from, well, matter hitting the antimatter when all these particles collided and annihilated. Most of space is empty space. Between the galaxies in intergalactic space, there's around 1 atom per cubic meter, which is just billions and billions of times less than air. So we'd be able to see this with our space telescopes. We'd be able to see the collisions between the matter and antimatter frontiers. So it seems very likely that there aren't big regions of the universe that are dominated by antimatter. Although it's not completely disproved yet, after all, we can only observe a fraction of what might exist in the universe. Physicists launched the Alpha Magnetic Spectrometer into space a few years back. What this can do is detect different types of particles. It's like a particle physics observatory in outer space. If the AMS had detected a big hunk of antimatter, for example an antihelium, well, that would change everything. Antihelium is too complicated to reasonably be produced by natural collisions and processes that make antimatter in the universe around us. They tend to just create individual particles. But antihelium is unlikely to form by itself. If we saw antihelium, the reasonable explanation would be that it drifted from some part of the universe dominated by antimatter, where antiatoms find it easier to form, or that large amounts of antimatter did survive the processes in the early universe around the time of the Big Bang. So far, though, it's seen nothing. There is always the possibility that there is an anti-universe out there, somewhere beyond the part of the universe we can see, or that's too far away to ever reach us. Since it's impossible for us to observe anything outside of the observable universe, there could well be antimatter out there. But then you have to explain how it managed to end up so far separated from all of the matter. What process drove them apart before they could mix? After all, at least in terms of charged particles, the charges are opposite, so they should attract each other. Luckily for physicists, there's finally starting to be some evidence that such processes exist that, ever so slightly, favour matter over antimatter. And if these processes, or similar ones, occurred in the early universe, we might not need to imagine universes of antimatter somewhere over the horizon to explain the world that we live in. So for this, we turn to particle physics experiments like the Large Hadron Collider, which are often in search of something called CP violation. CP violation is a process where charge and something called parity in particle physics aren't symmetrically conserved in the process. In other words, maybe the matter process occurs slightly faster than the corresponding antimatter process. The laws of physics aren't quite the same for matter and antimatter, and so we can see how there might end up being a universe full of one of them, and not a universe full of annihilation between the two of them. And they have seen evidence for some of this in particle physics. At the Large Hadron Collider, they smash protons together at incredible speeds and energies. And the result is what's produced as a shower of secondary particles, produced as the energy from the collision gets turned into the rest mass of these new particles. Physicists can then fine-tune the energy of the collision by changing how much they accelerate the protons. And depending on the energy they put into the protons, they see different showers of secondary particles. Based on how these behave, they can work out things like the energy and the lifetime of the particles that are being produced, and what they might decay into, or what they might be decaying from. Now, the LHC has discovered dozens of very unstable, very short-lived particles, or resonances, that decay extremely quickly. By studying how a particular pair of these particles, the lambda B0 and its antiparticle, decay, physicists are pretty confident that they've seen CP violation. In other words, the particle and its antiparticle don't behave in exactly the same way. Could this kind of behaviour, in the crazy hot and dense conditions of the early universe, explain why there's more matter than antimatter? Explain why anything exists? Maybe. This is just one example of a CP violation process. There are several different ones, and they all seem wildly obscure. They're not obvious at all. But they do exhibit this strange asymmetry, which may be responsible for the fact that anything exists at all. Philosophically, I quite like the idea that some obscure corner of physics might have such weighty consequences. Otherwise, would anyone care that some particle lived a few nanoseconds longer than its antiparticle, or whatever the case may be? But no one has a convincing model for it yet. These little bits of CP violation might not be enough to explain the excess of matter, which after all was big enough to create everything in our universe that we can see. The jury's still out. If you can conclusively solve the problem, there's probably a Nobel Prize in it. So aside from being mysterious and mysteriously absent, what is antimatter good for? And if it annihilates everything it touches, how can we make and store it? Let's talk about the recipe for producing antihydrogen. When you smash particles together in a particle accelerator, like the LHC at CERN, you get a shower of antiprotons produced as a result sometimes, along with loads of protons, and electrons and positrons as well. But these are all produced at incredibly high energies, travelling very close to the speed of light. To capture them before they recombine or smash into matter and annihilate, you have to be smart. You have to rely on how charged particles behave in magnetic fields. When you apply a magnetic field to a charged particle that's moving, the particle feels a force that's called the Lorentz force. This force is always at right angles to the direction that the particle is travelling, and the direction of the field, and the force depends on the charge of the particle too. So you can imagine that by applying a carefully chosen magnetic field, you can separate out these particles, which are being forced at different rates, and have different masses, which means they also accelerate at different rates, into different zones. The trick then is to slow down the antiprotons until they're slow enough to capture, and they do this by ramming them through a gas of electrons, which slows them down through collisions and through the electromagnetic force. At this point, they're cool enough and slow enough to form stable atoms of antihydrogen, if they then zoom into a zone with lots of positrons. The naked antiprotons can capture positrons, and then you have this strange antihydrogen atom, a positron with a positive charge whizzing around a negatively charged antiproton. The antiproton atom, the antihydrogen atom, has peculiar magnetic properties, and a carefully shaped magnetic field, or magnetic bottle as it's sometimes called, can keep them confined in a particular region for a while. It's much easier to confine them when they're moving slowly, which is why decelerating them is so important. So you make sure that the region has no pesky matter to annihilate with. You make sure that it's a good vacuum. With no matter to touch, they won't annihilate, for a little while at least. In 2011, physicists got very excited because they managed to store antihydrogen for 16 minutes. That's the record, I think. So you'd better take your data readings fast. It doesn't sound like much, but that was actually 10,000 times longer than the previous attempt. Long enough that they could actually hope to study the atoms properly. Back in 2011, the only way to know for sure that you'd captured antihydrogen was, well, the moment you'd no longer captured it. Doesn't it always seem to go, you don't know what you've got till it's gone? Well, physicists could detect the flash of energy when the antihydrogen annihilated on the walls of its magnetic prison, and at that point they figured, okay, we must have had one there for a bit. Since then, things have advanced, and they're now able to measure how it reacts to light by zapping it with photons from a laser. And they've confirmed that in this respect at least, matter and antimatter are exactly symmetric. They respond to light in the same way. The antihydrogen looks exactly the same as the hydrogen would. It has the same spectrum. It took 20 years since the first time they created antihydrogen to measure its spectrum, and only to confirm what we suspected already, which goes to show the amazing persistence of physicists. Plus, experimentalists like to look for black swan events. The really exciting experiment is the one that smashes up your theory, because it means you've discovered new physics. Or you've made a terrible mistake, but maybe new physics. If it had been different, perhaps the antimatter-matter asymmetry problem would be solved, but not yet. So I know what some of you are probably thinking. There's this incredibly destructive substance that can convert all of its matter into energy. It explodes with more force than an atomic bomb. We say that it literally annihilates matter. So, to quote Professor Death from those Mitchell and Webb sketches, could there be some kind of military application? Of course, people have thought about it. Dan Brown, the author of one of the world's most charity-shopped novels, The Da Vinci Code, until it was cruelly knocked off by 50 Shades of Grey, he even wrote a book where someone tries to blow up the Vatican with an antimatter bomb, powered by a simple gram of antimatter. In principle, the idea works, and it's pretty scary. But with the way we produce antimatter currently, there's simply no way you could possibly create this bomb. I'll quote a CERN physicist explaining why not. Take Dan Brown's hypothetical 1 gram of antimatter, says Rolf Landau. With present CERN technology, we would be able to produce 10 nanograms of antimatter per year, at a cost of around $10 to $20 million. Then we would have to deal with the problem of how to store so many particles. Billions upon billions of antiprotons. Obviously, it would take 100 million years and $1,000 trillion to make 1 gram. This appears ambitious even for the US military. Obviously, nuclear weapons exist that could do the same job way cheaper. It would take CERN 2 million years at present to produce antimatter enough for a Hiroshima-type explosion, and they'd have to be really careful not to drop it. Even if you imagine that you can suddenly mass-produce antimatter in a really cheap way that allows you to cram it into a bomb, it's still not much better than nukes. One thing you can say for nuclear weapons, at least the newer ones, is that they're mostly fail-safe. You might remember from our Teotwalki episodes on nukes that a nuclear weapon is set off when a core of radioactive material is explosively compressed, setting off a chain reaction that leads to an explosion. It used to be the case that this disastrous compression was done with some conventional explosives, but even then you have to very carefully shape the explosives so that they get the proper chain reaction that will go supercritical and give you a nuclear explosion. Nowadays they're much safer. There's very few ways that this could happen by mistake. It requires an intentional detonation. In other words, if you leave a nuclear bomb alone for 100 years or kick it, it won't explode, although I can't advise it. But antimatter is a completely different story. If, even for a fraction of a second, you stop powering the magnetic bottle, the magnets that hold it in place, the antimatter hits the cell walls and annihilates. That's fine if you just have a tiny amount. But if you have a Hiroshima bomb yield of antimatter explosives, it's very dangerous. And given that the sum total of antimatter that's been produced so far is about as destructive as lighting a match, I can't see people investing, even the military, in these inefficient death traps. But there is some hope for you if you're in love with the asymmetry of antimatter. For a start, in limited doses, it has already had some incredible uses. In PET scanners, for example, positrons, the antiparticles for electrons, are already used to great effect because their emissions could be seen. People dream that in the future, someday, antimatter could be used to fuel spaceships that will go on interstellar voyages. The reason why they want to use antimatter is that, after all, it's one of the most efficient fuels you can imagine. All of its mass is converted into energy, not some tiny fraction, like in the case of nuclear fuels, or fuels that you have to burn. And that means you have to launch a spaceship with less weight, which makes it easier to send up there. But the main problem with this will already probably be obvious to you. After all, whatever contains your fuel will need to be very carefully managed to prevent a catastrophic explosion. And if your spaceship is fueled by tiny explosions, there are obvious engineering problems that may preclude this from being ideal. So there we have it, the ghostly alternative to ordinary matter, an unsolved mystery at the beginning of the universe, a strange anomaly which allows, well, anything to exist at all. Annihilation as a force for destruction, but also possibly as a tool we could harness in the future. Antimatter, the anti-symmetric counterpart to the world around us, continues to fascinate and delight. Just don't shake hands with your anti-self if you ever happen to spot them. Thank you for listening to this episode of Physical Attraction. If you've enjoyed the show, follow us on Twitter at PhysicsPod. You can go and join the Facebook group over on Facebook, search for Physical Attraction. We have a page you can like as well, where people also discuss the new episodes. If you've enjoyed the show, please consider donating to us. There are plenty of ways you can do this. You can subscribe to our Patreon, www.patreon.com/physicalattraction. You can go to paypal.me/physicspod and give a one-time donation. Those who subscribe or donate more than $3 will receive access to at least one bonus episode, and they're really fun. I really enjoy creating those, and I think people enjoy listening to them too. So that's one way you can help us support the show, pay our hosting costs, and maybe, hopefully, reward me for some of the work I do in producing the show. If you can't do any of that, though, you can like us and review us on iTunes. That's always useful. Or you could just tell one other person about the show. Because, as I keep saying, if you all tell one other person, the power of exponential growth takes over. And within a few shows, we've got billions upon billions of listeners. And once we have billions of listeners, I will become incredibly wealthy and powerful. And then I will buy you a drink. Until next time, be kind to each other.